problem we're going to solve using differential equations is the Newton's law of cooling problem. The problem states that thermometer reads 18 degrees Fahrenheit, is brought into a room having temperature 70 degrees Fahrenheit. 1 minute later, the thermometer reads 31 degrees Fahrenheit. Let T of T equal the thermometer reading at time little t. First thing we're going to do is set up and solve a differential equation to find the function capital T of little t, which is giving the temperature reading on the thermometer at time little t. And the second thing, once we get that equation, is we're going to find the time at which the thermometer reading is 50 degrees Fahrenheit. So to start with, we're going to use Newton's law of cooling, which says that the instantaneous change in the temperature with respect to time is proportional between the object's temperature and ambient temperature. The ambient temperature is the room temperature, so I'm going to let T sub A represent the ambient temperature or the room temperature, which is the temperature of the surrounding medium. And it says in the problem that the ambient temperature or room temperature is 70 degrees Fahrenheit. So this means the differential equation that models the object's temperature says dt, d capital T, d little t, which is the instantaneous rate of change in the object's temperature with respect to time, is proportional, so it equals K times, it's proportional to the difference between the temperature of the thermometer or the object's temperature and the ambient temperature. So let's go ahead and I'll go ahead and substitute 7 degrees in for the ambient temperature, and we will solve this differential equation. The solution is going to be a function which tells the object's temperature at any time t. So let me just summarize kind of the facts that are going to help us from that, reading that equation. It did say that the initial temperature of the thermometer was 18 degrees Fahrenheit. Also, we had that the ambient temperature is 70 degrees Fahrenheit. And the problem said 1 minute later, the thermometer reads 31 degrees Fahrenheit. So we know the temperature of the thermometer at time 1 minute is equal to 31 degrees. The next thing we're going to do is solve this differential equation. Let me go ahead and put the ambient temperature in, although we can just solve it with TA, but I know the ambient temperature is 70 degrees. This differential equation is now separable. So I'm going to separate the capital T's on one side and the little t's on the other side, which is going to give me d capital T over K times capital T minus 70 is equal to, if I multiply both sides by d little t, I'm going to get that expression. So what I've done is I've separated it. It was a separable differential equation, and now I can integrate both sides. This can also be solved by looking at it as a first order linear differential equation with capital T as a function of little t. If I integrate both sides, on the left-hand side, the 1 over K is a constant, so that comes out. If I integrate d capital T over T minus 70, that is the natural log of the absolute value of T minus 70 degrees. And on the right-hand side, I get little t plus the constant C. So the next thing I'm going to do is multiply both sides through by K. And I'm going to get ln absolute value of T minus 70 is equal to K times T plus, I'm going to get K times C. I'm just going to call K times C a new constant, C1. Then if I exponentiate, raise both sides to the E, I get absolute value of T minus 70 on the left-hand side equals e to the kt times e to the c1. I'm going to call e to the c1 c2. The other thing that I can notice is that because my object is at initial time 18 degrees, the room temperature is 70 degrees, the thermometer is going to be heating up. So this expression is going to be the object's temperature, the thermometer's temperature is always going to be less than 70. So I'm going to have a negative on the left-hand side. So to make that, actually I don't even need to worry about that because I have a constant over here. So I'm going to drop these absolute value signs. If I really wanted this left-hand side to be positive, I could write it as 70 minus t. But that negative will be absorbed into this constant C2. So let me keep that information on the top because I'm going to need it to solve for my constants. And then we'll rewrite the differential equation. It is going to be t minus 70 is equal to C2e to the kt, and then I get t is equal to 70 plus C2e to the k times t. Now I'm going to use my two conditions to solve for the constants C2 and k. Using the initial temperature, t at 0 equals 18, I get 18 is t of 0, which is 70 plus C2 times e to the k times 0. And then that becomes 18 equals 70 plus C2. This is e to the 0, which is 1, which tells me that C2 is 18 minus 70, which is negative 52. 18 minus 70. Yeah. And then I'm going to use the other initial condition, t of 1 equals 31, to solve for C2. So far I know that I have that t is equal to 70 plus negative 52 for C2, e to the k t. And I'm going to use the other initial condition to solve for k. The initial condition that the time at 1 minute is 31 degrees. So I know that 31 is equal to t of 1, which equals 70 minus 52 e to the k times 1. And if I subtract a 70 from both sides, I get a negative 39 equals negative 52 e to the k. And to solve for k, I'm going to leave that red differential equation up there, so I just need to solve for k. I divide both sides by negative 52. I'm going to get 39 over 52 is equal to e to the k, and then I can natural log both sides. So ln of 39 over 52 will equal k. And so using my calculator, I can 39 divided by 52, and then I can natural log that. And that ends up being negative 2.23 decimal places. I get negative 0.288 for my constant k. And so the function t of t, which expresses the thermometer's temperature as a function of time, is equal to 70 minus 52 e to the negative 0.288 times t. And that's going to be the solution to part A. Part B asked when the thermometer will read 50 degrees. So I need to substitute in 50 degrees for the temperature and solve for the time. So to do that, I can subtract the 70 from both sides and get a negative 20. And then I'm also going to divide by this negative 52. And then I can natural log both sides. So I'm going to get negative 0.288 t is equal to the ln of 20 over 52. And then I can divide both sides by negative 0.288. So 20 divided by 52. And I get 3.32, so about 3.3 minutes is when the thermometer will read 50 degrees.